Open controls. Activate. Default. Open controls. Activate. Default. Open controls. Screen particles on a one-dimensional lattice. There are left arrows labeled by alpha and right arrows labeled by beta. If two particles are next to each other, there are no arrows between them. Image. The generator of the simple exclusion process can be explicitly written. In the most elementary case where there are two lattice sites, then there are four possible configurations. Associate to each particle the vector. Page 13 of 51. 1 table. Table start. Column 1, 1. Column 2, 0. Table end. Math. Double tap to view math in full screen. The generator of the simple exclusion process can be explicitly written. In the most elementary case where there are and to each whole, i.e., a non-particle, the vector. 1 table. Table start. Column 1, 0. Column 2, 1. Table end. Math. Tensoring the vectors together, we can associate to each configuration a canonical basis element of the four-dimensional vector space. C circled times C. Math. Double tap to view math in full screen. C circled times C. Math. Double tap to view. The field here is chosen to be the complex numbers because it is algebraically closed, although of course probabilities are real numbers. With that set up, the generators then 4 times 4. Math. Matrix. 1 table. Greek letter alpha table start. Row 1, column 1, 0. Row 1, column 2, 0. Row 1, column 3, 0. Row 1, column 4, 0. Row 2, column 1, 0. Row 2, column 2, -1. Row 2, column 3, 1. Row 2, column 4, 0. Row 3, column 1, 0. Row 3, column 2, q squared. Row 3, column 3, -q squared. Row 3, column 4, 0. Row 4, column 1, 0. Row 4, column 2, 0. Row 4, column 3, 0. Row 4, column 4, 0. Table end. Math. 1 table. Greek letter alpha table start. Row 1, column 1. The constant. Page 14 of 51. Page 13 of 51. The constant. Toggle navigation button. The field here is chosen to be the complex. With that set up, the generators that page 14 of 51. Page 13 of 51. The constant. Page 14 of 51 can be viewed as a time rescaling, so it can be removed without loss of toggle navigation button. Navigation. Page 13 of 51. With that set up, the generators then toolbar show bookmarks. The field here is chosen to be the complex numbers because it is algebraically closed, although refresh button. Toggle navigation. Navigation. Landmark. Collapsed. The field here is page 14 of 51. Page 15 of 51. Page 16 of 51. Page 15 of page 14 of 51. Page 13 of 51. Can be viewed as a time rescaling, so it can be the constant. Page 14 of 51. Page 13 of 51. Can be viewed as a time rescaling, so the constant. Page 14 of 51. There's refresh button. There are corresponding can be viewed as a time toggle cellular 2 and 4 ASCP and Yang backs can be viewed as a time rescaling, so it can be removed without loss of generality. Page 15 of 51. Page 14 of 51. Page 13 of 51. The constant. Can be viewed as a time rescaling, so it can be removed without loss of generality. Page 14 of 51. In a more general setting, where there are n lattice sites, the generator can be defined from the above. 4 times 4. Math. Double tap matrix, which we now denote L. The generator is now a 2 superscript n circle times 2 superscript n. Math. Double tap to matrix and axon. C squared. Superscript circle times n. Math. Double tap to view math in full screen. Define L subscript I plus 1. Math. Double tap to view math in full screen. By 4 terms L subscript I plus 1 equals I subscript 2 superscript I minus 1 circle times L circle times I subscript 2 superscript n minus 1. Math. Double tap to view math in full screen. 4 terms L subscript I plus 1 equals I subscript 2 superscript I minus 1 circle times L circle times I subscript 2 superscript n minus 1. Math. Similar notation using subscripts will be used throughout these notes. ASCP and Yang-Baxter equation. Heading 3.2. Heading level 4. ASCP and Yang-Baxter equation. Heading level. The corresponding notion of integrability in the quantum case comes from Yang-Baxter equation. It was shown 3 in page link. That when a matrix solves the Yang-Baxter equation link, there are corresponding commuting transfer matrices, which are analogous to conserved quantities in the classical setting. Page 15 of 51. Using the same notation as in the previous section, we say that a vertical scroll bar. 48. Using the same notation as in the previous section, we say that a matrix braided Yang-Baxter equation solves the braided Yang-Baxter equation if R subscript 1, 2, R subscript 2, 3, R subscript 1, 2 equals R subscript 2, 3, R subscript 1, 2, R subscript 2, 3. Math. Double tap. Somewhat confusingly, this equation is also sometimes called the braid equation or just the Yang-Baxter equation. An equivalent formulation is over R subscript 1, 2 over R subscript 1, 3 over R subscript 2, 3 equals over R subscript 2, 3 over R subscript 1, 3 over R subscript 1, 2. Math. Where over R equals P composed with R. Math. And 4 terms Px circled times Y equals Y circled times X. Math. Double tap permutes the tensor power exercise left to the reader. A visual representation of YB is given by this image. The left-hand side has 3 lines labeled 1, 2 and 3. The strand labeled 1 is above the strand labeled 2 which is above the strand labeled 3. At the intersection of strands I and J is Rij. Read from bottom to top is R1 2 R1 3 R2 3 which is the left-hand side of the Yang-Baxter equation. On the right-hand side the middle strand labeled 2 has moved over and it now reads R2 3 R1 3 R1 2 which is the right-hand side of the Yang-Baxter equation. Image. R12 R3 page 15 of 48. In some settings, the YBE occurs in the scattering of particles with quantum mechanics considerations, such as the QISM, quantum inverse scattering method. Given an arbitrary matrix R, one can check that it satisfies the YBE through direct computation. However, it may be more helpful to consider some simple examples first. If P, V circled times V right arrow volts circled times V, math. Double tap denotes the permutation operator which sends U circled times V, math. Double tap 2. V circled times U, math. Double tap to view math in full screen. Then the braided Yang-Baxter equation becomes an identity of transpositions. 6 terms, 12 composed with 23 composed with 12 equals 23 composed with 12 composed with 23, math. Double tap to view math in full screen. Page 17 of 51. This identity holds, since both sides equal the permutation. 13. Math. An even more simple solution is the identity matrix. A probabilist may remark that a permutation matrix and an identity matrix are both examples of a stochastic matrix, albeit somewhat trivial examples. It may then be natural to try to find more general stochastic matrices which solve the Yang-Baxter equation. The simplest generalization occurs when capital V, math, is two-dimensional, with basis E, subscript 1, E, subscript 2, math. Using exclusion processes as a prototype, we can define the operator R, subscript Greek letter alpha Greek letter beta, math. Double tap by 5 terms, R, subscript Greek letter alpha Greek letter beta, E, subscript 1, circle times E, subscript 1, equals E, subscript 1, circle times E, subscript 1, R, subscript Greek letter alpha Greek letter beta, E, subscript 2, circle times E, subscript 2, equals E, subscript 2, circle times E, subscript 2, math. Double tap to view math in full screen. And 1 table, table start, row 1, R, subscript Greek letter alpha Greek letter beta, E, subscript 1, circle times E, subscript 2, equals 1 minus Greek letter alpha E, subscript 1, circle times E, subscript 2, plus Greek letter alpha E, subscript 2, circle times E, subscript 1, row 2, R, subscript Greek letter alpha Greek letter beta, E, subscript 2, circle times E, subscript 1, equals Greek letter beta E, subscript 1, circle times E, subscript 2, plus 1 minus Greek letter beta E, subscript 2, circle times E, subscript 1, table end, math. Double tap, inserting this matrix into the Yang-Baxter equation and evaluating. A probabilist may remark, inserting this matrix into the Yang-Baxter equation and evaluating at page 18 of 51. E, subscript 1, circle times E, subscript 1, circle times E, subscript 2, math. Double tap to view math in full screen. 1 finds that Greek letter alpha 1 minus Greek letter beta equals 0, math. Double vertical scroll bar, 48 pages, page 16 of 48, page 17 of 48, is a necessary requirement for a solution to YBE, evaluating R, subscript Greek letter alpha, 1, math. Double tap to view math in full screen. R, and R, subscript 0, Greek letter beta, math. Double tap at E, subscript 1, circle times E, subscript 2, circle times E, subscript 1, math. And E, subscript 2, circle times E, subscript 1, circle times E, subscript 1, math. Yields no additional equations. Exercise left to the reader. One could also evaluate YBE at the 3 vectors. E, subscript 2, circle times E, subscript 1, circle times E, subscript 1, math. One could also evaluate YBE at the 3 E, subscript 1, circle times E, subscript 2, circle times E, subscript 1, math. E, subscript 1, and E, subscript 1, circle times E, subscript 1, circle times E, subscript 2, math. Double tap, but instead we use another symmetry of ASEP. This is called, in words, in an ASEP, particle hole involution. In words, in an ASEP with drift to the right, the holes evolve as an ASEP with drift to the left. Symbolically, we define an involution of capital V, math, which switches E, subscript 1, math, and E, subscript 2, math. Then 4 terms, T, superscript circle times 2, R, subscript Greek letter alpha, Greek letter beta, T, control center. Selected, screen record.